In this video, we are going to take another look at the existence and uniqueness theorem. In particular, we will look at the differential equation y prime equals f of ty. So notice this can be linear, it can be nonlinear, with the initial condition y of 0 equals 0. So it's an initial value problem. So our theorem says if f and df dy are continuous on a rectangle, and here our domain is a rectangle since y prime depends on two variables, t and y. So our domain is two-dimensional, where t, the absolute value, is less than or equal to a, and y, the absolute value, is less than or equal to b. So if f and df dy are continuous on this rectangle, then there is some interval, absolute value of t is less than or equal to h, which is less than or equal to a. So you notice this interval for t is smaller than our domain, in which there exists a unique solution y equals phi of t of the initial value problem. So in short, it says that this differential equation has a unique solution if f and df dy are continuous. We are then going to look at the integral equation, which is equivalent to the differential equation. And by equivalent, I mean solutions of this integral equation are also solutions of the differential equation. And the reason why we do this is in case our differential equation cannot be solved. We don't have a method for solving this differential equation. What we can do is use this integral equation in a method called the Picard method of successive approximations to approximate a solution. And the way we use this Picard method is we start with phi naught is equal to 0. We take that from our initial condition. Then our subsequent phi n plus 1 is equal to the integral from 0 to t f of s phi of n. That means we base our new estimate based on our old estimate ds. And then you notice this here is exactly our integral equation, which is equivalent to our differential equation. There are some conditions for termination, and I will say that the Picard method of successive approximation is not difficult. It's very much a kind of plug and chug into the formulas, so that'll go pretty quickly. But there are some questions about this method of successive approximations that involve a number of proofs to prove, which, to be quite honest, are beyond the scope of this class, of this course. So we'll outline them, and some of them will seem very hand-wavy, and others that aren't hand-wavy, they'll seem very, there's lots of detail, lots of nitty-gritty in it. And so I will summarize them here, and I will also summarize when we get to even the more detailed explanation of this chapter and further down into this video. I will summarize them and give you the option at the end of the video to follow some of them a little more closely. But anyway, the three questions we have: do all members of the sequence exist, or may this process, the Picard method of successive approximation, does it break down at some time? And the answer is it can break down. So to ensure that it doesn't break down and that members of the sequence exist, we're going to limit our domain. So initially, f and df dy are continuous on this rectangle. So our domain is going to be a small portion of that rectangle. In particular, it's going to be, we're going to limit t so that it's less than or equal to h, and y, where it's less than or equal to b, that's kind of the same, where h is equal to a or b over m, where m is the maximum that our derivative can be on this interval. So we take our maximum value of the derivative, b over m, and then we choose either a or b over m, whichever is smaller, to limit our t. And that will ensure that the sequence exists, that we can keep computing these. Does the sequence converge? And we do an example where we show that the sequence straightforwardly comes to show the convergence of the sequence. To show the convergence of the sequence straightforwardly comes down to showing convergence of a series using the ratio test. But in general, it can be more involved, and we have a few hints towards that. The third question: what are the properties of the limit function? In particular, does it satisfy the integral equation? And the short answer is yes. the sequence satisfies the integral equation because of uniform convergence. Or not the sequence, but the limit of the sequence satisfies the integral equation because of uniform convergence. And the last question, is this the only solution or may there be others? This refers to uniqueness. In general, to show uniqueness, if we feel like we have two solutions, phi of n and y of n, if we want to show uniqueness, we must show that phi of n must equal to psi of n. And we do have an example of this detailed, worked out, but it can be a very detailed, tedious process. And I said one of the parts that is very straightforward and doesn't involve a lot of tedious detail is the Picard method of successful approximations, and we will do an example of that. We have the theorem of existence and uniqueness for first-order nonlinear equations, which we had seen in a previous video, but we'll go through it again. So let the functions f and the function df dy be continuous on some rectangle where t goes between a and b, so that's our domain for f, and y goes between c and d, that's our domain for our derivative, and it contains the point t naught, y naught. Then in some interval t between t naught minus h and t naught plus h, contained in the interval t from a to b, there is a unique solution y equals phi of t of the initial value problem, y prime equals f of ty, y of t naught equals y naught. Summarizing what that means is if you have this first order differential equation, it will have a solution that will be unique if f and df dy are both continuous. One thing to note, here it says that there is a unique solution in some interval, and it doesn't say it's necessarily the interval where f and df dy are continuous. It's just in some interval contained in where f and df dy are continuous. So it could be possibly a smaller interval. In looking how to prove this, for linear equations and some other special cases, such as the one that we have looked at, which is like separable equations and exact equations, the existence of solution can be established by actually solving the problem, and then you can point to the solution and say, here it is. However, in general, this approach is not feasible because so many differential equations just cannot be solved. There's no method of solving the differential equation that applies in all cases. Therefore, in the general case, it's necessary to adopt an indirect approach that demonstrates the existence of solution. But often these indirect approaches do not provide a practical means for finding a solution. So we can prove the solution might exist, but it's not constructive in that it doesn't tell us how to find the solution. So in this video, what we're going to look at is the Picard method, and the heart of this method is to construct a sequence of functions that converge to a limit function satisfying the initial value problem. So the sequence of functions, each of these functions that we are using to construct, to look at the limit, so the sequence of functions may not solve the initial value problem, but the limit of the sequence will. So it's not always possible to determine the limit function except in a few rare cases, and we do not go into the details of the proof. However, we will indicate its main features and point out some of the difficulties that must be overcome. So when we look at this proof, we're going to do a slight simplification. We are going to look at first order, possibly nonlinear equations, but we're going to set the initial value equal to 0. So y naught is equal to 0. Then our theorem says if f and df dy are continuous on a rectangle, where t is, and it's a rectangle because we have two variables, f depends both on t and y, so t is, the absolute value is less than or equal to a, the absolute value of y is less than or equal to b, then there's some interval t between h and a, so this interval for t is definitely less than a and possibly smaller than a, in which there exists a unique solution of the initial value problem. So again, the simplification is we set the initial value, we're saying in f and df dy are continuous, then there's some interval where this differential equation will have solutions and they will be unique. And there's a note, because we have this simplification where we set the initial value equal to 0. So if some other initial point is given, we can always make a preliminary change of variables corresponding to a translation of the coordinate axis that will take the given point to the origin, which we're not going to do today. But we'll just note that even though we have this simplification, it can be overcome. And last, which I believe I've already mentioned, the theorem states there's some interval in which there is a solution. So this interval may be smaller than the interval that f and df dy are continuous. And that is reflected here. So the absolute value of t is not only less than or equal to a, it might be less than or equal to h, which is less than or equal to a. Here I have the new theorem of existence and uniqueness that's simplified with this y naught equals 0 written out here. And for the method of proof, it's necessary to transform the initial value problem into a more convenient form where you're going to transform this differential equation, an equation involving derivatives, to an integral equation, an equation involving integrals. So suppose we have a differentiable function y is equal to phi of t that satisfies the initial problem. In other words, phi of t is a solution to our differential equation. Then f of ty, and in this case we replace y with phi of t, is a continuous function of t only, since phi is only t. Hence we can integrate from the initial point t equals 0 to an arbitrary value of t, and phi of t will be the integral of, and then plugging in our derivative function, f of s, phi of s ds. And phi of 0 is equal to 0. Since the equation above contains an integral of an unknown function, it is called an integral equation. And the integral equation, this is not a formula for the solution of the initial value, but the initial value problem here and the integral equation here are equivalent in the sense that any solution of one is also a solution of the other. So in other words, instead of solving for this equation, we can solve this integral, and whatever solutions phi of t solves this equation will also solve the original differential equation. And take a look, read through that slowly until it makes sense to you. And then what we are going to do is do a Picard method of successive approximations. Remember, our approach is to construct a sequence of functions that converges to a limit function that will be the solution. So we're going to successively approximate the solution and hope in the limit we actually have a solution. So a method of showing the integral equation has a unique solution. We're going to start with an initial function that satisfies the initial condition. We'll just say our phi naught of t is equal to 0. So at least our initial condition is solved. And then we're going to iterate. For our next phi function, we're going to integrate from 0 to t f of s phi n of s ds. And then if we end up, we can terminate, we repeatedly iterate until either phi of k plus 1 is equal to phi of k, or in general, we can see that our infinite sequence will converge. And then we have these questions here that are important to answer. Do all the members of the sequence exist, or may the process break down at some stage? Does the sequence converge? What are the properties of the limit function? In particular, does it satisfy the integral equation? Is it actually a solution? And is this the only solution, or may there be others? And we will go through first the Picard iteration, and then we'll investigate these answers or these questions right after we have an example of a Picard iteration. So our first example is y prime, or dy dt, is equal to 2t times 1 plus y, where y of 0 is equal to 0. So our integral equation is going to be phi of t integrating between 0 and t, and then just plugging in s, since s is our variable of integration, 2s, 1 plus, and now we're going to plug in phi of s. So this is our integral equation. Again, we start, where is this? We start with phi 0 of t is equal to 0. That's our initial value. Now we iterate, so we're looking for phi 1, and that's when n is equal to 0. So phi 1 of t is the integral from 0 to t. Now we plug in f of s with phi of 1. So that's 2s times 1 plus phi naught of s ds. I'm sorry, it wasn't phi 1, it was phi naught. Phi naught. So here I can plug in then for my phi naught, which is equal to 0. So I have the integral from 0 to t, 2s, 1 plus 0 ds, and then you integrate, you plug in, and you get t squared. Now I continue my iteration for n equals 1 so that I can get phi 2, plugging into this formula here. So phi 2 will be 0 to t, my f of s, and then phi, if I'm at phi 2, I'm looking at phi 1. So that's 2s times 1 plus phi 1 is equal to t squared, so I put in s squared ds. So I integrate, and I get t squared plus 1/2 t to the 4th. When I look for phi 3, using the same kind of pattern, I have my 2s, 1 plus, and then I plug in my previous phi, s squared plus 1/2 s to the 4th. I get t squared plus t to the 4th over 2 plus t to the 6th over 2 times 3. And if you remember this kind of pattern, especially if you remember doing sequences and series in first year calculus, that was like after you did differential integration, you often did sequences and series. So this here is the pattern of t squared plus t to the 4th over 2 factorial, t to the 6th over 2 times 3, that would be 3 factorial. So eventually we get t to the 2n over n factorial. And this formula can be proved by mathematical induction, but we're not going to do this in this class. We are just going to hand wave around and say we recognize the pattern that's going on. And if n3 didn't make the pattern clear, you might do n equals 4 and a couple of more things until you see the pattern. So I've rewritten my integral equation here. This is my phi of t, and I saw the pattern is equal to t to the 2n over n factorial. But of course I'm summing all this up, so I wrote it in my summation notation. So k equals 1 to infinity, t to the 2k over k factorial. So the limit does exist. And see, now you have a summation. And remember that stuff in sequences and series and calculus, the very end of calculus. So we want to know when this series converges, when the sum converges. And we can apply the ratio test, and we can see that this series converges to 0 as k approaches infinity. So it converges for all t. And for your reference, in case you forgot what the ratio test was, so if you wanted to know if a series, a to the n, converges, it converges at the limit of n, as n approaches infinity, of an plus 1 over an is less than 1. So you can do that here. We have an plus 1, so that's 2 to the 2 times k plus 1, which will give us 2k plus 2, all over k plus 1 factorial, and then divided by an. And so I have an, but I already used the reciprocal here. An is just k factorial over 2 to the 2k. You can simplify, you get t squared over k plus 1, which as k goes to infinity, you can see that this will approach 0. So it does converge for all t. So looking over here at the Picard method, we were never going to get the termination because phi of k plus 1 equals phi of k, but we did see that the solution was a series, in other words, a solution of some sequence, and then, a summation of a sequence of terms, and that by applying the ratio test to the series, we could see that it did converge. So we did answer the question here. Does a sequence converge? And the answer is yes. Also, if you recognize this as a Taylor series, and you might have recognized that if you remember your first year calculus, since phi of t is a Taylor series, then it can be differentiated or integrated term by term. And we can verify that phi of t is a solution to the differential equation. So here What are the properties of the limit function? In particular, does it satisfy the integral equation? The answer would be yes. So the answer, let's see, the answer to question 1, do the members of the sequence exist or may the process break down? You can do this forever. You could have kept finding more terms. So that's fine. It does not break down. The members of the sequence exist. It does converge. It does satisfy the integral equation. Last, is it a unique solution? So that's something we need to worry about next. Oh, but before we talk about uniqueness, one other point. You might recognize this also again from your first year calculus class, that this is e to the t squared minus 1. And if you don't recognize it, that's okay. You can just take my word for it. So what we've done, and I've summarized our work on that example of the Picard iteration right here, is we've used the Picard method of successive approximations to come up with our phi of n, look at the limit of our sequence of phi of n, and then we found that it converges, and then it converges essentially to the solution of our integral equation, which is then the solution of the differential equation. And so in this way, we have shown the existence of the solution because we've essentially produced a solution. Now that we have shown a solution to our differential equation, we can ask if the solution is unique. And actually, I'm going to defer this discussion till we talk about, in general, not just for this example, but in general, how we determine uniqueness. And we're going to use this as our example. And the only thing I will say at this time is that in mathematics, the way you generally try to show that there's a unique solution is you assume there are two solutions, and we are going to call them phi and psi. And then what you need to show in order to prove they're unique, that the solution's unique, is you need to show that phi is equal to psi. Even for our particular example, the process is it's rather detailed and has a lot of different parts. And so that's one of the reasons why I'm going to go ahead and save that as our example at the very end. In general, for any differential equation, we're talking beyond our example. When we start this process, the questions we want to look at are, do all the members of the sequence exist, or may the process break down at some stage? Second, does the sequence converge? Third, what are the properties of the limit function? In particular, does it satisfy the integral equation? And last, is this solution the only solution, or may there be others? In other words, is it unique? The details of the proof of the existence and uniqueness theorem and some of the details in these proofs might be a little bit beyond this course. And then others, like this last one here, it isn't so much beyond this course as there's a lot of detail and a lot of different steps in there. But nevertheless, we will go through each one and see what we can come up with. Starting with the first question, do all members of the sequence exist, or may the process break down at some stage? So in the previous example that we had with the numbers, f and f dy were continuous on the whole ty plane, and each member of the sequence could be explicitly calculated. In general, however, f and f dy are assumed to be continuous only in a limited interval. In other words, our domain is going to be a rectangle. The absolute value of t is less than or equal to a, and the absolute value of y is less than or equal to b. And to show you what that looks like, here's the drawing. And just to remind you, our function is dy dt. So dy dt is a function of t and y. So our domain is two-dimensional, where we're centered around the initial value point. Remember, we start with phi of 0 is equal to 0. So we're starting at the initial value point, so we're centered there, and t is thought to be, we're continuous in this direction between negative a, and we're continuous in the y direction between negative b and b. So we're given this rectangle where we know the function is continuous. So our function doesn't have to be continuous everywhere to have a solution, but it needs to be continuous on some interval, or rather on some rectangle. But now the members of the sequence cannot as a rule be explicitly determined even though we have this continuity. And the reason is we have continuity with this domain, but at some stage, for example, at the n equals k stage, so after we've calculated our phi of k, when we did our calculation of phi of k, we might have stayed in this domain to plug in for our f of y and t of y, but then our solution might have taken us out of the domain because, when you have a domain and range, they don't have to be equal. You start in the domain and then you have a range. So in this case, we might have started in the domain, but our function might have taken us out of the domain. And once it takes us out of the domain, when we compute our next term, phi of k plus 1, we're outside where we know f and f dy are continuous. So in this case, when we try to calculate phi of k plus 1, we're using points where it is not known to be continuous or maybe doesn't even exist, which would make the calculation impossible. So this is our potential problem. And what we do to solve this problem is to restrict t to a smaller interval. Remember when I first introduced in this video existence and uniqueness, I said that there would be some interval which there exists a unique solution, but I also said that it doesn't necessarily have to be the same interval where we have continuity. It could be a smaller interval. So this is the danger we're avoiding when we make that statement. So we're restricting t to a small interval. And the way we find such an interval is we make use of the fact that a continuous function on the closed bound region is bounded and hence therefore exists and has a maximum value of that function, so that we call m. So what is this saying here is if we have a continuous function, we can look at a closed interval. So if we're looking between these two numbers, and we know our function is not asymptotic or something, then we'll always be able to find a maximum. In this case, the maximum's here. Or if our function looks like this, our maximum might be here. This will mean, since ft of y is the slope or the derivative, this means our maximum slope of the graph of this equation is m. So since the graph contains the point 0, 0, again, because that's our initial value, the graph must be at 0, 0 with slope m. So here I have my negative m, here I have my slope positive m, and intersecting with this graph, I get kind of this bow tie area. Hence, our next point in our sequence will remain in R as long as R is contained in the bow tie shaped region. And we only consider the rectangle D now as our domain, that the absolute value of t is less than or equal to h, and absolute value of y is less than or equal to b, where h is equal to a or b over m, whichever is smaller. And with this restriction, all members of the sequence exist. So these are the two important values for h. So this is our new domain. And actually, that's also what we have up here in our theorem. The short answer to the first question, do all the members of the sequence exist? We say that to ensure the members of the sequence exist, we limit the domain to t, the absolute value of t is less than or equal to h, and the absolute value of y is less than or equal to b, where h is equal to a or b over m, whichever is smaller, with m equal to the max of the derivative on the rectangle that was given where f and df dy are continuous. Answer the question, does the sequence converge? In other words, the sequence of all our phi of n's, if we look at them as a sequence, do they converge? We're going to look back at our example. And in our example, here was the original differential equation. It turned out that phi of n, just because of the way the example worked out, was equal to this sum, or this series, which we could then prove using the ratio test that the series converged. Now, in general, there's no guarantee that the differential equation is going to yield a series. So what are we going to do? And this is really quite clever. Actually, on the last proof, I was a little bit snarky when I really have no right to be, because some mathematician much more intelligent than I was able to prove it. And honestly, I wouldn't have been able to prove that last theorem on my own. So, but so actually, in its own right, it's a lovely proof. But here, I hope you can appreciate the cleverness of this. So we're going to create a series, and we're going to do that using a telescoping series. If you've heard of that before, that's great. And if you haven't, we'll talk about it. So we have phi n of t is equal to phi 1 of t plus, and this is our next term, phi 2 of t minus phi 1 of t. So here you can see these phi 1 of t's will cancel out, plus phi 3 of t minus phi 2 of t. So this one will cancel with this one. And then we keep going, and here you see like the last term inside the parentheses cancels with the previous term, right? This last term inside these parentheses cancel with the previous term. So here at the very end, we're going to have phi of n of t minus, and this one will cancel with the previous term over here, whatever's in parentheses. So we've created this telescoping series, and it's called telescoping because even though it ends up being long, it collapses down to, in this case, phi n. So we created our series, and this series here for phi n is the nth partial sum of phi 1 is just here, and then we wrote our formula for what's inside these parentheses, which is phi k plus 1 minus phi k, and then of course we create the summation of all the different k equals 1 to infinity. So now the convergence of this sequence is established by showing this series here, converges. And to do this, we must estimate the magnitude of phi of k plus 1 of t minus phi of k of t. So the remainder of this proof is quite involved and also left as an exercise in your textbook, so I'm going to leave this point right here. The question, what are the properties of the limit function? In particular, does it satisfy the integral equation? So let's start by saying another important question before we go to whether or not it satisfies the integral equation is whether or not the solution is continuous. And continuity is not necessarily a consequence of the convergence of the sequence, even though each member of the sequence is itself continuous. So one way to know the solution is continuous is to show the sequence not only converges, but it converges in a uniform manner, which we're not going to discuss here because that's a whole nother topic. But we should know when we proved convergence in the sequence, it was enough to establish uniform convergence, and hence the continuity of the limit function in the interval. Just to kind of summarize that again, proving continuity of the solution in this course it's really kind of beyond this course, but so we'll just say that when we proved convergence of the sequence, that's enough to guarantee continuity of the limit function on the interval. What we do want to look at is, does the solution satisfy the integral equation? So I've written down from our Picard method how we solve for phi of n plus 1. So we have the integral from 0 to t f of s, phi of n of s ds. So we want to look at the limit as n approaches infinity, right? Because we're looking on what it converges on. And in general, you cannot just move the limit inside an integral. You can't change the order of a limit in an integration. But because the sequence converges uniformly, we can do this. So in other words, take my word for it. So, but don't do this in general. Don't think because I've done this here, you can generally do it. But let's move the limit inside. So what we get then, it's this phi of n that is dependent on n. So we move the limit over to the phi of n of s. So we have phi of t is equal to 0 to t f s. And then our limit here is what this converges to, which is phi of s ds. So the limit of our process of these of our sequence of phi of n as n goes to infinity is equal to f of s, the limit of, as n approaches infinity, of f n of s. And hence our solution satisfies the integral. For the last question, is this the only solution, or may there be others? In other words, is the solution unique? We are going to use our last example, y prime is equal to 2t times 1 plus y. Okay, so now we can go on to uniqueness. So if you want to show that a solution to an equation or problem is unique, the standard way to do this in math is to assume there are two solutions, and then later, you do some work to show that phi, your first solution, has to equal to your second solution. In other words, they're really the same thing. So if you have two solutions, they're really equal to each other. Or you'll find some sort of contradiction if you have two solutions that tells you that, well, actually there must have only been one. We're going to start by assuming two solutions, that we have a phi and a psi. And we're going to show that out of necessity, phi has to equal to psi. We'll start with two solutions, phi and psi, and we'll assume they are not equal. In other words, we truly do have two solutions. Of course, we're going to end up with some sort of contradiction or something that says actually they have to be equal. But we'll start by saying they are not equal. Then that means for some t, there's at least one t where phi of t minus psi of t does not equal to 0. So we're going to consider this phi of t minus psi of t, and we're going to plug this into our equation here. So what we will get is the integral to s, and then we have our phi of t, and because we're using s as our variable of integration, that will be 1 plus phi of psi, and then we're subtracting psi of t. So again, using our variable of integration and this formula here, and it's a minus psi of t, so we'll have minus 1 minus psi of s ds. And then the 1's cancel out, and we get 0 to 2 pi 2s times phi of s minus psi of s ds. And here's where things get a little bit tricky or fancy, whatever you want to say. So we'll just say we're getting fancy. So the idea is here, it might be difficult to show equality, but sometimes it's not as hard to show a less than or equal. So we put in this absolute value in order to get a less than or equal. And then because we're actually trying to show equality, what we want to show is looking at certain aspects of this equation will show that the left-hand side has to be less than or equal to the right-hand side. But then we'll look at other aspects of the equation, and we'll see that the left-hand side has to be less than or equal to the right-hand side of the equation. And assuming both of these conclusions were correct, the only way both of them can exist at the same time is if we have equality. So to reiterate, we can show equality by showing that both of these conditions, the left-hand side has to be less than or equal to the right-hand side, as well as the left-hand side has to be greater than or equal to the right-hand side. And sometimes these inequalities are easier to show than the equalities. So we introduce an inequality by putting in the absolute value. And now we can take the absolute value of both sides of the equation. So we have the absolute value of the left-hand side equals to the absolute value of the right-hand side. But now just looking at this absolute value has to be less than or equal to, if we take the integral of the absolute value of what's inside. So remember, this only works because of this less than or equal to. It wouldn't be equal to. You can't just move around or exchange the integral and the absolute value, except for the fact of this less than or equal. Oh, and also it has to be that t is greater than 0. The next thing we want to do in our fancy proof, or our tricksiness, I don't know, is get rid of this 2s. We're going to do this first by letting we're going to restrict t to be in the interval 0 to a over 2. And this 2 comes because we're going to get rid of this 2s. You'll see in a minute. So anyway, where a is arbitrary. So we're going to focus on this small interval. A is arbitrary. T goes from 0 to a over 2. And from this equation, t is less than or equal to a over 2. We get that 2t is less than or equal to a. So now just looking at this part, phi of t minus psi of t, the absolute value of that is less than a times our integral without this 2s. So 0 to t, phi of s minus psi of s ds. So exactly where did this come from? Well, I have my integral of 2s, absolute value, phi of s minus psi of s. So I wrote that down here, copied it here for reference. So I'm going to integrate using integration by parts. I have u is equal to 2s, v prime is equal to the absolute value of phi of s minus c of s. Now my u prime, fortunately, is just equal to 2. That's easy. And my v, actually, that's not too bad. It's the integral of my derivative. So far, so good. So doing integration by parts, then my integration here is equal to u times v. So I wrote that down right over here, u times v. And then I have minus, what is it, u prime, u prime times v. So here I have u prime 2, and I have v written down here. Looking at this, so I have the integral of phi of s minus psi of s. So I can kind of factor my 2s minus 2 times my integral phi of s minus psi of s ds. And this here, I can drop the 2 because remember, I'm only worried about proving that less than or equal and then proving later greater than or less than. So this is certainly less than 2s, right? 2s minus 2 is going to be less than 2s. So what I have is phi of s minus psi of s is less than 2s phi of s psi of s, right? Because my original equation was over here, which is less than a, because 2s or 2t is less than or equal to a. This is less than a integral phi of s minus psi of s. So this is where I get this equation here from this equation. It's all this blue stuff, basically integration by parts. Okay, so I've gone from this line to this line here. So I have my absolute value of phi of t minus psi of t is less than or equal to a times, except I changed it, to the integral from 0 to t phi of s minus, phi of s minus psi of s, absolute value ds. But this equation here is a linear differential equation in disguise. To see that, we're going to let u of t equal to this portion, the absolute value of phi of s minus psi of s. I've brought down my u of t, and I wrote what it's equal to here. Then I can also observe that u of 0 is equal to 0, because if I plug in t equals 0, I'm integrating from 0 to 0, so I get 0. I can also observe that u of t is greater than or equal to 0 for t greater than or equal to 0 because of the absolute value. And then if u of t is equal to the integral of this, then u prime of t is just what's inside the integral. And now what I have is u prime of t, if I subtract this a minus u of t from both sides of the equation, I'll get u prime of t minus a u of t is less than or equal to 0. Now you can see that I have a linear differential equation. So it was in disguise here, but by using the u of t, it's easier to see. And it's linear, so I can solve it using an integrating factor, e to the minus at. So I did that here, and my solution is e to the minus at u of t is less than or equal to 0. And what that tells me is, since this is positive, that means u of t must be less than or equal to 0 on the interval from 0 to a over 2. But a is arbitrary, so that must mean u of t is less than or equal to 0 for all t greater than 0. Now, that would imply that the derivative of u of t is also equal to 0, and looking at that definition, setting this equal to 0, that would imply that phi of t is equal to psi of t, and we are done. So please don't roll your eyes, but my short summary of this is defined if we have a unique solution. In general, we assume we have two solutions, phi of n and psi of n, and we must show that phi of n is equal to psi of n. So if you went through the entire proof, then you know that there's a lot to this proof. I don't know if you feel you gained a lot of wisdom by going through that, but I will say you did learn a few techniques and a few interesting tricks. But just as a bonus, I am going to share some wisdom with you, and it comes in the form of a joke. So here it is. This is my last topic for this. It's like a bonus topic for this video, and it's a joke. So at a university, there's this well-known professor always studying, trying to get to the truth, learning things, proving things. And one day, a genie comes to him, poof, and says, I will grant you one of three wishes: infinite beauty, infinite wealth, or infinite wisdom. And of course, the professor, having always pursued knowledge his whole life, chooses infinite wisdom. And poof, they are instantly wise. And news of this spreads throughout campus. And some graduate students come to the professor and they say, "Professor, please share some of your wisdom with us." And the professor looks at them and says, "I should have taken the money." And to recap what we did in this video, we looked at the existence and uniqueness theorem. We looked at the differential equation, which potentially could be linear, it could be nonlinear. Y prime is equal to f of ty with the initial condition y of 0 equals 0. And we said there is a solution to the initial value problem, y equals phi of t, if f and df dy are continuous on a rectangle where, and it's a rectangle because the domain of dy dt is a function of two variables, t and y. So the rectangle for our domain is the absolute value of t is less than or equal to a, and y, the absolute value of y, is less than or equal to b. Then we know there's a solution on some interval where t is less than or equal to h, which is less than or equal to a. And we saw the reason for this. It'll be on the next slide. Okay, then the next thing we did is to prove this, we kind of wanted to demonstrate a solution, and that would prove existence. However, for many differential equations, we cannot necessarily solve them. So what we used is the Picard method of successive approximations. And part of this was looking at the integral equation, or essentially the Picard method uses the integral equation, which looks like phi of t, and that's the same phi here, that's the solution, is the integral from 0 to t, f of s, phi of s ds. And the idea of this integral equation is it is equivalent to this differential equation, and that any solution of the integral equation will also solve the differential equation. So the Picard method of successive approximations start with phi of 0 is equal to 0, and we get that from the initial condition. And then from there, we get a series of functions, phi of n plus 1, using the previous phi of n, to compute our next function. So we have a series of functions, none of which solve our differential equation, but the limit of our series of, of our sequence of phi of n, we can find a solution. We did an example of this Picard method, which was very straightforward. And after we did that one example, we looked at in general, for Picard method of successive approximations, at these questions to kind of determine what we can expect from the Picard method of successive approximation and how successful will we be in trying to prove existence and uniqueness. And the questions were, first, do all members of the sequence exist, or may the process break down at some stage? And the answer to that was we would ensure that all the members exist by limiting our domain to the absolute value of t is less than or equal to h, and the absolute value of y is less than or equal to b, where h is equal to a or b over m, whichever is smaller. So that's what this is over here in our theorem. So whichever is smaller, when m is equal to the max of our derivative on the rectangle where our function and df dy are continuous. The second question, does a sequence converge? And in our example, it was very straightforward to show it converged because we got a series, and then we used the ratio test to prove convergence. In general, this can be quite involved, and we didn't go through a whole lot of detail. A few little points were made about this. The third question, what are the properties of the limit function? In particular, does it satisfy the integral equation? And this proof was a little bit beyond this course, but we did say the sequence satisfies the integral equation because of uniform convergence. And then last, is the solution the only solution, or may there be others? And we did use our example to show uniqueness, but it was quite involved. And we started by showing if we have two solutions, phi of n and psi of n, then we must show that phi of n is equal to psi of n. And this is a general technique for showing uniqueness in mathematics. And that's it for this video. Thank you for watching.